So we've talked about what happens when you throw a ball straight up in the air. Right? The ball goes up, it slows down until it turns around and comes back down. Right? That's free fall, right? Even though it's not falling the whole time, it really is. It's accelerating downward the entire time. We also know what happens when you throw a ball, say, to the right. Right? It travels following uniform motion, meaning constant velocity motion. But what happens when you throw a ball at an angle? So that would be like this guy. Well, it turns out it does both motions at the same time. That's not what I wanted to do. It does both motions at the same time. Right? So in the vertical direction, it goes up and it comes back down. And in the horizontal direction, it just keeps going. Right? So it's a path kind of like this. Right? That motion is something we call projectile motion. In fact, I'll just label it here. Right? And it's really just motion under only the action of gravity that includes motion that is not just in the y direction. Right? So how do we describe projectile motion? Well, I know how to describe this motion with the free fall equations, and I know how to describe this motion with the uniform motion equation. So projectile motion is really just both of those at the same time. So projectile motion is those two sets of equations at the same time. Okay, so what were those equations? Well, we can go back to the equation sheets, and they're right here, actually. So these equations right here, this is free fall. Come on. There, now I can write on it. And this is constant velocity. So these two sets of equations together describe projectile motion, and you'll notice they contain different variables with the exception of time. Delta t is the only common variable between these two sets of equations. And you could say that, well, there's a Vx and a Vy, and I would say yes. And those are both related to the velocity that I drew on this other page. Here. So this is my V initial. Let me change my color here. This is V initial. But it's off at some angle, right? I meant to change the color. There. There's some angle theta. So V initial is actually made of Vx and Vy initial. Let's move that over. Back over to Vx and Vy initial. Now I don't bother to subscript Vx with initial and final because Vx is constant. Right? Vx is not changing because there's no acceleration in the x direction. So initial and final and everywhere in between is the same number. But y is definitely changing. It's getting smaller and then bigger if it's pointing up initially. Okay, so let's see how this plays out in a problem. I'd like to look at example number, see if we can find it, 5. So an arrow is fired at a 40-degree angle with an initial speed of 50 meters per second. How far from the starting point does it land, and what will be its maximum height? So let's draw a picture. And I'm going to start maybe with some axes. There's a y-axis and an x-axis. And I'll draw my initial velocity. It's at 40 degrees. So there's 40 degrees. We could label that as theta. And it's 50 meters per second. Now, as before, as on the other page, that 50 meters per second does describe this velocity. But if I'm going to plug this into projectile motion equations, I need this broken into the x bit, so there's vx, and the y bit, which is vy initial. Right, so we could just do that math. I know that I'm going to have to do that math eventually, so I might as well just do it now. So let's do that over here. So Vx is, that looks like the adjacent side of that right triangle. Do you see the right triangle there? So this is the hypotenuse, and this is the adjacent side. Let's make those 3 lines go away, 4 lines go away. All right, so that's just V times cosine of theta, which is 50 meters per second times cosine of 40 degrees. That turns out to be 38.3 meters per second. And then Vy initial must be the other side of that triangle. It's a sine of 40 degrees, right? So that's 50 sine 40 degrees, which is 32.1. I'm not worrying about sig figs here. I may not worry about sig figs much at all, but I definitely don't worry about it in intermediate steps, because if I round every calculation, I'm going to accumulate some kind of error by the end of the problem. So I don't round until the very final answer, right? The thing I put in a box. Okay, so what does this motion look like? Again, it's a parabola. So it's something like that. We can make that look a little nicer. Sure. Not quite symmetric, but that's okay. Is this really a parabola? I mean, it looks like a parabola, the way I drew it, more or less. But is it really a parabola? And the answer is yes. This is technically a parabola. We know that vertical position, y versus t, is definitely a parabola because the equation that describes it is the equation of a parabola. And if you solve the x direction equation for delta t and plug it into the y direction equation, I can get y as a function of x, and that's definitely parabolic. Just for our information. Okay, so what am I solving for? Well, I see a how far, and then I see a duration. No, I don't. I see maximum height there. How far and maximum height. So how far is that? In fact, it's this distance. That's a delta x. And maximum height is this distance, called y max. So those are the two things we're solving for. So let's start with delta x. Let's start with finding delta x. So find delta x. Okay. So let's go back to the equations, and in fact, I think I drew this. Oh, I may have erased it. Fine. I'm going to write the list of the two sets of equations here. So in the y direction, let's use a different color. In the y direction, I have y final equals y initial plus vy initial delta t minus half g delta t squared. I have a vy final equals Vy initial minus G delta T, and Vy final squared equals Vy initial squared minus 2G delta T, delta Y. So those are my three equations in the x direction, in the y direction, and in the x direction. I just have one equation, x final equals x initial plus Vx delta T. Again, there's no need to subscript the Vx with initial or final because it's constant. And I do need to remember that I cannot plug x direction information into the y direction equation. So I have a Vx. I can't plug that anywhere into the y direction equations. That's a very, very common mistake for students to make when first learning about this. So I'm just cautioning you now. Okay, so what am I solving for? Let's circle it. I would like to know x final. I know x initial is 0. I would like to know y final for a different part of the motion. Does that make sense? Right? If we go back to our handout here. There are two things we're solving for, the delta x and the y max. But they happen at different points in the motion, so they're going to have different delta t's associated with them. But because this is a parabola and it's symmetric, the way we're starting and ending at the same height, the delta t's are related by a factor of 2, which will be nice to remember. Okay, so I'm looking for delta x, I'm looking for y max. What do I know? I know x initial because I chose it to be 0. I know y initial because I chose it to be 0. In fact, let's write those things down. Let's write down, what do I know? Let's say given x initial is 0, y initial is 0. I also know y final is 0, right? At least for the motion that describes this range, right? Find delta x goes from the beginning of this to the to this endpoint over here. So the y position there is 0. I know Vx, it's a number, it's 38.3. And I know Vy initial as 32.1 meters per second. Again, have to be very careful not to plug these into the wrong equations. I'm fixing my 8. There, it's a little better. What else do I know? I know G is 9.8 meters per second squared. And again, the negative sign I put in explicitly. So if I call G negative here, that's actually going to screw things up. Okay. This is great, except, so we'll go back to our list of equations. I think I put it under scratch. And I can say, okay, what do I know? I know x initial. I know Vx. I know y initial. I also know y final for this part of the motion. I know Vy initial. I don't know Vy final. I know Vy initial here. I know G. So I'm kind of left in a pickle, and I'll tell you why. Let me erase that. I would like to find this variable, right? But I can't use this equation. This is the only equation that x final shows up in, and I don't know delta t. So that's two things I don't know in one equation that leaves me in a bind. So I need to find delta t first. All right, so I need to find delta t first. Is there an equation here that lets me find delta t? Well, I don't know Vy final at the end of the trip. So I can't use this equation and I can't use this equation. But look, I can use this guy because delta t is the only thing I don't know here. All right, so I'm going to take that equation back over to the other page. I'm going to make some of my markups go away so that we can use these again later. Okay, that's fine. Okay, so we just gained a little insight into the procedure we're going to have to follow here. Oops. So we can't find delta x directly, but we are going to have to find, oops. So we are going to have to find something else first. There. Find delta t first. And then we can go back and find delta x. So the equation we decided we were going to be able to use is y final equals y initial plus vy initial delta t minus half g delta t squared. Y final is 0. We're at the ground ultimately. Y initial is also 0 because we started at the ground. So we ended at the ground, we started at the ground. Vy initial is a positive 32.1 meters per second times delta t minus half times 9.8 times delta t squared. So I'm not putting units in here. If you want to, that's totally fine. Mostly I'm not putting in units because I ran out of space. But also, I know that if I plug everything in SI units, that it'll come out in SI units. The answer will come out in seconds if I put this in meters per second and meters per second squared. Okay. So this is just algebra at this point. We can solve for that. It turns out, so this is quadratic, right? So there are two answers. One of the answers is delta t equals 0. That's not useful. Clearly, it doesn't take 0 time to get to the other end. But that is one of the places where position is 0. So delta t equals 0 is a solution. It's just the trivial solution. The other solution is that delta t equals, let me find it here. I've worked this in the past. 6.559 seconds. 6.559 seconds. Okay, so that's not our answer. Maybe I shouldn't put a box around it, but I could underline it twice. That's our intermediate step. And now I can plug that into the x direction equation. So the x direction equation, remember, was x final equals x initial plus vx delta t. All right, so x initial is 0. Vx was 38.5, I think. 38.3 meters per second times 6.559 seconds. That gets me a distance, and that distance is 251.2 meters. 251.2 meters, which I'm going to shorten to 2 sig figs. Everything we've done here has been multiplication, right? And I guess technically that 50 probably only has 1. But I'm going to say keeping 4 seems like too much. 2 seems right. That's a little hand wavy. But I feel okay about it. 250 meters. Okay, is that reasonable? Yeah, that seems pretty reasonable for the range for an arrow. Okay. So there's the first part of our problem. The second part of the problem is how high does it go? What's its maximum height during this flight? And that's a different delta t. Do you see that? Y max happens at half of the trip. And half of the trip should take half of the time. All right? That argument is a little dicey because you could say, well, to reach half of the maximum height, does that take half of the time? And the answer is it does not. But half of the range, since that rate is constant, does take half of the time. The other thing you can say is this trip is parabolic. So the trip up and the trip down should be exactly symmetric. Right? There's another way to solve this, but I don't want to take the time to do it right now. We'll talk about it another time. So the next part is find Y max. And I'm gonna say this, that we can now say delta t to the top of that, to the apex of that path is the time that we solved in the previous step divided by 2, right? Which is, I didn't write it down, so we'll calculate it quickly. 6.559 divided by 2 is 3.28 seconds, rounding a little bit. 3.28 seconds. And we're looking for a y final. There's only one equation that has y final in it. Let's go back to look at the equations. There's only one equation that has a y final in it. And that's this top equation right here. So that's what we're going to use. Vy initial is something I know. Delta t is something I just solved. So this will work. Nope. So we'll fill it in right here. Y final equals y initial plus Vy initial delta t minus half g delta t squared. Okay, so y final is what we're solving for. Y initial, y initial is 0. My markings went away. Fine, we'll write it again. Y final equals y initial plus Vy initial delta t minus half g delta t squared. Okay, so y initial is 0. Vy initial is that 32.1. I'm going to leave out the units to save some space here. Delta t, we just solved that as 3.28 seconds minus half times 9.8 times 3.28 squared. And if you do that math, you get 52.7 meters, which I'm going to round to 53 meters, which seems about right as well. Okay, so I think that's good for this example. There are other ways to approach this. So the equations that we used here, it has to be this set of equations, but they don't have to be used in quite this way. And we'll talk about that another time. So thanks for watching.